In an earlier unit, we studied polynomials and rational functions. Now we're going to take limits of these rational functions and draw on our knowledge of rational functions and polynomials to make sense of the concept of a limit so that we can go on then to derive the concept of the derivative. So right now we're just going to focus in on 6 different types of limits that we can get with these rational functions, and then end with the one that is most important, realizing that we aren't wanting to use them to draw rational functions. We already know how to do that, but to use our knowledge of rational functions to make sense of what we're doing here algebraically. So let's start with limit summary. The limit, if it exists, is the value that y approaches as x approaches a given value. Which means if y doesn't approach a given value, then there isn't a limit. If y does not approach a particular value, then the limit does not exist. So that is simply it. Either as x approaches a given value, y approaches a given value, the limit exists, or as x approaches a given value, y does not approach a given value and the limit does not exist. So let's look at our first examples here. In all of these, we are looking at what happens to f of x as x approaches infinity, as x gets infinitely big. Now you might recognize this as the endpoint behavior from rational functions. We had 3 different cases where the degree of the numerator was higher, where the degree of the denominator was higher, and where the degree in the numerator and the denominator were equal. In each case, we're going to see what happens as x goes to infinity. So let's examine those numerically first. So down here I have a spreadsheet where I have put in 1, 10, 100, all the way up to this large kind of crazy number for x. So these are x equals. And then these are my y values. Y equals these values. So when x equals 1 for my first function, y equals negative 0.8. But what I'm interested in seeing what happens is what happens as x gets infinitely big. So as x gets bigger and bigger and bigger, what is happening to y? And you'll notice that as x is getting bigger and bigger and bigger, y is also getting bigger and bigger. So as x goes to infinity here, we have y goes to infinity. Second example, as we put in values, bigger and bigger values for x, notice that y is getting smaller and smaller and smaller. So as x goes to infinity, y goes to 0 here. And for the third example, as x gets bigger and bigger and bigger, y gets really, really close to the number 0.2. Y is approaching the number 0.2 as x gets really, really big. So let's go back and see how we could figure out these particular outcomes without actually looking at a spreadsheet. So first of all, let's recall that when x is getting really, really big, the term in the numerator and the term in the denominator with the highest degree will dominate the value of the numerator and the denominator. In other words, when I put in a really big number for x, like a billion squared is so much bigger than negative 3 billion and negative 2 that these terms don't really make any difference in the overall size of the number. Of course, when I add 4 to a billion, 4 is not going to make much difference either. So x squared and x determine really what happens to the size of this number. So I could say that the limit of my original function is really equivalent to the limit of x squared over x as x goes to infinity, which of course is equivalent to the limit as x goes to infinity of just x. So in other words, we're saying that the equation x squared minus 3x minus 2 over x plus 4 is really equivalent as far as going to infinity as x just representing, as y just being equal to x. In other words, very similar to just being equal to x. It's not exactly equal to x, but it's very similar. So we're just saying as x goes to infinity, y goes to infinity. As x gets bigger and bigger, so does y. So since y is not approaching any particular number, we say the limit as x goes to infinity does not exist. Y does not approach a particular number. Y does not level off or approach a particular number. It just keeps getting bigger. So the limit does not exist in this case. Now, second example. That's where we saw down here that as x goes to infinity, y gets close to 0. So once again, let's look at our highest degree term in the numerator and our highest degree term in the denominator. So this is approximately equal to the same limit we would get as if we had the limit as x goes to infinity of x over x squared, which could be simplified to the limit as x goes to infinity of 1 over x. Now this is a little more clear. If we put in very large numbers for x, 1 over x is going to get very, very close to 0. So we saw that as x goes to infinity, y gets very close to 0. So we say the limit as x goes to infinity is 0. So in the first case, the limit did not exist when the numerator has a higher degree than the denominator. In the second case, when the denominator has a higher degree, the limit's going to be 0. This corresponds to no horizontal asymptote in number 1 and a horizontal asymptote of 0, or the x-axis, in 2, when we were looking at our rational functions earlier. Number 3, we saw down here that as x goes to infinity, y goes to 0.2. Well, where did the 0.2 come from? Once again, let's look at the highest degree terms in the numerator and the denominator. In this case, they have equal degree. So we can say the limit as x goes to infinity of x squared over 5x squared. Well, reducing that fraction, we get limit as x goes to infinity of 1/5. In other words, as x goes to infinity, y equals 1/5, or 0.2. So as x approaches infinity, y approaches 1/5, or 0.2. So we say the limit as x goes to infinity is 0.2. So those are the 3 cases where x goes to infinity. In the next video, then, we'll look at the 3 cases when we put a particular number in for x.